Hello, Mr. Collier here. This is the third video for Lab 7C, which is about efficiency. In this video, I'm going to show you how to analyze the data that we've collected. In this lab, we were looking at the efficiency of our track system by sending a car down the track through a photo gate and having it bounce off a rubber band and go through the photo gate a second time. Based on how the speed changes between the first and the second pass through, we can look at how much energy is lost to the system. In this video, I'm going to show you how to do the calculations using the data from the Part 2 video. So for our first series of trials, we were manipulating the number of marbles that were in the car, and then we got the before and after the bounce times. And you'll notice that the after bounce is always a slower or longer time. That's because some energy is lost to the system, and so the car goes slower. So I filled in the mass of the car, which we're going to need a little bit later when we do kinetic energy. But first we want to do the speed of the car before the bounce. The speed of the car is calculated by doing 0.01 meters, which is the size of the flag, and we're dividing that by the time through the photo gate before the bounce. That gives us a speed of 1.45 meters per second. The kinetic energy before the bounce is found by using 1/2 mv squared, and that is 0.5 times the mass of the car times the speed that I just calculated squared, and that'll give us an energy of 0.0603 joules. Now we're ready to calculate the speed after the bounce. Again, distance divided by time. The distance is the 0.01 meters. That's the flag of the car. We're going to divide that by the time. The after time is 0.0078 seconds, which gives us an after speed of 1.28 meters per second. Again, the kinetic energy is 1/2 mv squared. So again, 1/2 the mass of the car times the speed we just did squared, which gives us a kinetic energy of 0.0470 joules. Finally, we're going to look at the efficiency of the system. Efficiency is found by looking at the work output divided by the work input. In this case, the work output is the kinetic energy after the bounce, and the work input is the kinetic energy before the bounce. So we plug those numbers in, work output divided by work input times 100, and we get an efficiency of 77.9%. One last reminder for this set of calculations, your mass is changing in this first section, so don't forget to change the mass in the calculations as you go. In your second set of calculations, instead of changing the mass, you were changing how far the thumb screw was screwed in, which ultimately changes your initial launch speed. I'm not going to go through a full set of calculations for this next data table because it's the same as the first one, but I will just remind you of the equations. The speed before and after the bounce is 0.01 meters divided by the time. The kinetic energy before and after the bounce is 1/2 mass times velocity squared, and the efficiency of the car is the work output divided by the work input times 100, where the output is the energy after the bounce and the input is before the bounce. You're going to be making two graphs, and I'm not going to set them up for you completely this time. I want you to try that on your own for this lab. But the first graph is going to be efficiency versus mass, and the second graph is going to be efficiency versus the speed before the bounce. So basically one graph for each of your two sets of data. And that's it for Lab 7C. You'll see how the mass affects the efficiency and how the initial launch speed affects the efficiency. Good luck.